So I'd like to begin by telling you about the contents of this course. We finished the intro last week, and today we'll be talking about the partition function. And afterwards, we'll be discussing a couple of state functions. So we'll be entering today's topic of the partition function. In German, the translation for partition function is Zustandssumme, which means sum over states. Okay, so the system gets partitioned according to states, or you partition the system and you take states into consideration. We begin with a subchapter where we'll introduce the notion of the ensemble. Ensembles are a fundamental concept in physical chemistry, and we need this concept to develop the underlying framework. You have already encountered pictures like this, where you would have an energy scale as a function of some degree of freedom, some variable of your system. And what you have encountered is that because of quantum mechanics, not all energies are accessible, but only discrete states, right? Now, what you have seen so far in quantum mechanics is just one system, one molecule, one atom, right? But we have many, right? We talked about this, Avogadro's number. So this is the question: how, with this Avogadro number, would we arrive at something like a phase diagram where you have pressure versus temperature? Then it might look something like this, right? Where this is your gas, liquid, and solid phase you're familiar with. So we can accomplish this with the help of the ensemble, but we first need a little bit of an idea about this dimensionality that's underpinning things. In particular, we want to look at the degrees of freedom, also abbreviated as DOF, for a system, right? So this system can be anything. It can be a quantum system, right? Can be an atom, can be diatomic, triatomics, can be a molecule like caffeine or nicotine molecule. So what we know is that in your reference frame in which your particles move, and we talked about that when discussing Newtonian mechanics, this reference frame, your particle will move here or here, and that's a translational movement, right? Now we have 3 dimensions in our space, so we have 3 translational degrees of freedom, right? So let's abbreviate that by tra. Then you also can consider that your particle will rotate, right? So that's our rod. And then there will be internal degrees of freedom if you have more than one atom, right? Your atoms will start vibrate and move with respect to each other. And those are the internal or vibrational degrees of freedom, right? And we can roughly consider every atom in your in your system, and you recall our little drawing of this trajectory here, where a bunch of points were evolving over time, and this bunch of points can be one system, right? And so for each point, you can have dimensions x, y, and z in which they can move. So formally, in total, you should have something like 3n degrees of freedom. And then we have 3 translational, we have 3 rotational, and then the number of internal degrees of freedom must be the difference of whatever's left. So we have 3n minus 6. Now that's the general case. However, we should consider a system that's of a funny shape, namely one shape where maybe 1 degree of freedom becomes irrelevant, right? And such a case is a linear system, right? If you imagine something in the shape of a rod, right, like this pen here, it can certainly rotate in this direction. It can certainly rotate in this direction. But if I rotate in the first dimension, I'm rotating it around its own axis, right? And if this is a truly cylindrical object, that degree of freedom is gone, right? It won't vary anything. So for linear objects, you would expect 3 translations, but only 2 rotational degrees of freedom. And correspondingly, your number of degrees of freedom for vibrations or internal movements is 3n minus 5. We can play this game once more. We collapse the rod into a sphere. And here again, we have 3. A sphere can rotate in all directions without changes. So we have 0 here and 3n minus 3 internal degrees of freedom. Okay. So this is a very important concept, and regrettably, and I'm afraid of that, you might not have heard about what's known as the vibrational normal modes of your systems. Have you? Anybody? No? So these are the movements of your atoms in terms of their own reference frame. It's fairly straightforward to obtain this. It's not incredibly complicated, and it's hugely important for you to imagine how things actually look like when your atoms move. What's shown here is the formaldehyde molecule. It has 4 atoms. So we have 3n minus 6 gives us 6 internal degrees of freedom. And you see here the frequencies in inverse wave numbers as you might encounter them in a vibrational spectrum. And each of these modes, and I'm going to start the animation now, is different from each other. It involves all atoms in the molecule. It carries different energies, right? And the way you have to imagine this is that these are the 6 dimensions which underpin the vibrational movements of formaldehyde. Along each of these dimensions, you can have discrete excitations, right? This is one dimension involving all atoms simultaneously, where you have the full quantum spectrum, right? Typically, people assume a harmonic potential, right? So the harmonic oscillator, you've learned how to solve. You can solve along that dimension, and all of a sudden, you get the vibrational excitation energy for each of these modes, right? So if you have a photon shooting in with something like 1250 inverse centimeters, this mode would get excited. This mode and only this mode, no other modes, right? That's where the interaction happens, okay? This is, if you are seeing this for the first time, it might blow your mind. That's okay. We all went through it. It's worthwhile, yeah, a meditation to come to grasp with this important structure of matter. You have analogous movements in solids. These are known as phonons, right? This is how atoms move. Are there any questions on this concept? You can also, of course, always ask your tutor if a question comes to mind only tomorrow or so. With this, stop this. I'd like to proceed. I hope this example has told you a little bit how these 3n-6 dimensions might look like. And coming back to this energy figure you see here with the discrete lines, you see now that this r coordinate here, this could be such a coordinate along which all atoms move. And for formaldehyde, you just saw 6 such coordinates. And so this means I can, I should give sort of a vectorial notation here to this R. I have 6 of these coordinates for formaldehyde. And in the 6-dimensional problem, I can get different quantum solutions, right? The beauty and the importance of these normal modes is that they decouple these movements, and you can solve Schrödinger's equation for each of them independently. And this is an approximation, but a very useful and common one, which also underpins a lot of what we'll be talking about in this lecture. So the dimensionality of your system is given by n being the number of atoms. And so what we have then is a Schrödinger equation again, where the Hamiltonian depends on this number of atoms, right? And this thing is being applied to your wave function. For example, the vibrational wave function. So the function that involves the movements of all the nuclei, right? So this Hamiltonian would contain a kinetic energy term for every atom moving like a billiard ball, right? And the potential energy in that Hamiltonian comes from the electrons interacting with each other, interacting with the nuclei, and the nuclei interacting with each other again, right? So that is also known as the potential energy surface. And so, or potential energy hypersurface, PEHS. Okay. Now, in that potential, we can solve for the frequency, the eigenvalue. That's the frequency in your infrared spectrum. Again, and so this is a vibrational Schrödinger equation. Now, it's very important for you to realize in quantum mechanics, it's a general physics theory. It applies to any system. That means it applies also to different degrees of freedom. You can apply it just to vibration. Then we have a Schrödinger equation for rotation, and we have a Schrödinger equation for translation of your system. And we have a Schrödinger equation for the electrons in the system, okay? We could also have a Schrödinger equation for this classroom, right? And there would be a wave function that involves all of us in a single wave function, right? according to quantum mechanics, that's not outrageous. So the question then is, how complicated is all of this, right? So suppose in each dimension, right? So in the case of formaldehyde, we had 6 dimensions. Suppose you want to get 10 points to construct some interpolation, some polynomial fit of this potential, so you can plug it in your vibrational Schrödinger equation, right? So let's suppose you have just 10 points here for each dimension. Well, so this would mean your potential energy, you would need something like 10 to the power of 3n minus 6 number of points, right? To get all the combinations for the full, to cover the full potential energy hypersurface with 10 points per degree of freedom. Okay. So you rapidly see that just for a modest number of atoms, your vibrational problem is already hitting a dramatic complexity, and that's also known as the curse of dimensionality. So just for your medium-sized organic molecule like caffeine or so, that's pretty bad, right? And we are talking just 10 points per dimension. That's not an awful lot, right? Now, things get worse as you say, well, the whole point of this course, why I'm sitting here today, is that we want to look at Avogadro number kind of systems, right? So what's going on? As I say, okay, my number of particles, roughly Avogadro's number, right? Well, the math is easy. So then you have 10 to the 3n minus 6 times Avogadro's number, times number of particles here, okay? So if we insert Avogadro's number, if the number of particles is, if we really deal with just a mole, right, then you have, so 6 times 10 to the 23, 6 times 3, 18, minus 6 times 6, 36, times 10 to the 23 in the exponent, okay? Sorry, I forgot the n. N minus 36. So consider H2O, n equals 3. Then this number becomes 10 to the 54 minus 36 times 10 to the 23. And that's the same as 10 to the 28 times 10 to the 23. Okay. So if we just wanted to naively imply the quantum mechanics you learned last semester to your bulk sample, which you're dealing with in the lab, you'd be basically doomed, right? It's 10 to the 10 to the 3, 23. So, so in other words, it's hopeless due to curse of dimensionality. Now, Fortunately, this is only a worst case scenario where really we had this example last week. You have 100 million molecules or so or systems in one dimension, right? So this is really required only if, as the first molecule wiggles, the 100 millionth molecule in this other dimension feels that wiggling and responds to it somehow, right? That's a pretty rare behavior, let's say, exotic kind of behavior in terms of vibrations. So long-range coupling of these vibrations is rather exotic. And so we can often, more often than not, safely assume that this thing is only a worst-case scenario. And we can successfully use something you hopefully discussed as well in your quantum mechanics course, the separation ansatz for the wave function leads to an additivity rule for energies of formally non-interacting particles. Okay? And you could imagine, you have a question? Just trying to figure out what the second word was. The second word? For psi. Separation ansatz for psi. Okay? Even if there's a misunderstanding, just raise your hand or ask. Others are probably struggling with the exact same words, so that's helpful. Now, you can imagine the system definition to be arbitrary. You could say my system is the water molecule, or you say my system is two water molecules, hydrogen bonded, right? So I have 6 atoms, right? And then I consider that my system and solve the problem. And then you can grow your system, right, in terms of more and more particles until the effect of non-interaction vanishes, right? So we can converge away this assumption of separation, and you would then have, obviously, the first neighbor will feel the vibrations of your first system, but the 10th neighbor maybe much less, and the 100th neighbor even less, right? And so you can systematically grow the size of your system until the non-interacting limit has been reached and you're satisfied, right? The idea that you have to go up to the 100 millionth neighbor is indeed, in most of the cases, not necessary. So what does this mean? These are just words, but of course we like to express this more rigorously. So this means your psi, and this is now the psi from our Schrödinger equation, where we did the psi for the total thing, right? So H, and now I have n particles times n number of atoms, Hamiltonian. This is my total psi with state J, with the total energy of state J for the total system, the 1 mole system. This psi I approximated by a product, right? And this product now runs over system I equals 1 until number of particles, okay? capital pi is the symbol for product, right? And I have a product of little phi's for each particle, okay? These little phi's for each particle, they belong still to state J. Okay? So for my state J of the total wave function, I now write it as a product of little phi's for the same state J, right? But these little phi's, they sit literally on each of these little molecules, right? So if you have, I mean, a liter of water has like 55 moles, right? So if you have 55 moles of water molecules, right, then this sum would run up to 55 moles, right? And you would have 55 moles of little phi's. But just for the state J, right? Now, if you make that ansatz, then and only then, your total energy of the state is exactly the sum of the energies of the individual molecules or systems. Okay. Now, what does this mean in number of points we would have? So we have a huge reduction in dimensionality. Right. In particular, your number of points now would correspond to NP times 10 to the 3ni. Sorry, the 3n minus 6. Right? So instead of having this as a factor in my exponent, I now have this as a factor of my base. So that's very nice. So we have interacting systems, but we still have the problem that all of this just holds for one state J, right? Now, what if, by pure coincidence, one molecule is vibrating in one state and the next molecule is vibrating in a different state? Right? And then you have a mole number of molecules, right? So this is the remaining problem. Oh, let's just say, but what about the NS possible states? Here I use the index J. Right? If I'd have to do this for every state, then this would mean I still have to deal with NP times 10 to the 3n minus 6 to the power of number of states, if I want to do all the combinations of possible states, right? So this is the question. This problem can be solved thanks to ensembles. Okay. So the whole course, the whole field of statistical mechanics, if you wish, in this introductory level, rests really on this first assumption that we can separate the wave functions. And then the second one is that we can use an ensemble notion. Okay. So far, so good. Any questions? Okay. So what is this ensemble? Ensemble is the French word for set or pool of systems, right? And they are supposed to be identical, right? It's a set or pool, if you prefer. And now we count the number of identical systems. And I'm sorry for that, but I'd like to use a different symbol for that. Before we use this NP, but NP was generic. Now we really formally say it's a set or pool of capital A identical systems. That means they all have the same Hamiltonian. Yeah? But we know, thanks to Schrödinger, that there are many solutions, right? So we have a system, imagine Avogadro's number of system, but each system, and it's pure, right? No mixtures, and each system can result in any one of the permissible solutions to Schrödinger's equation. So of identical systems, each in some state, and we like to use the index J, and in thermal equilibrium. With some heat reservoir and for A being much larger than the number of possible states. Okay, so we can make a little drawing of this. So imagine some insulating wall. And in this region, there's a thermal reservoir, right? So something that keeps your temperature constant. And in this reservoir, you have I equals 1, I equals 2, and so on. I equals I. And eventually you have I equals A systems. Okay. And each system can have a different state. So this is state J, state K, state J, let's say, and then again some state M, right? So this would be the system index on top and the state index on the bottom, right? And the whole thing is thermalized. Right? And so these A systems in this thermal reservoir, that's what we call an ensemble. Okay. So mathematically speaking, we have a set of systems and each carries an energy, and they have states energetic states, right, from Schrödinger's equation. This will depend on the volume and the temperature. So sort of volume in your system or size of your system, and you have in total A members in this ensemble, right? So our state I runs from 1 to A, and I'm sorry, here the I, this is the state, and for state we said J, and the state J, so J and I, the state J runs from 1 until number of states, okay? Now in Schrödinger's equation, it's open-ended how many states we consider, but we assume that generally speaking, your system will populate the lower states, right? So the number of states that matter will be finite, right? So you can always choose the capital A to be larger than that number. So the key question now is, can we understand this ensemble? In particular, as we said before, right, this explosion here with the number of states, is this somehow tempered, or is this, can we keep this under control by allowing the states to go up to as many states they want to populate, but thanks to Avogadro number kind of systems, maybe the distribution is not so bad, right? So that's the next question. What is the distribution of states in the ensemble? So basically, what we want to do is to start counting, right? So in particular, we consider the number of systems that happen to be in some state J. And this number, we shall call this number AJ. So if I have my state here, and I have the number of systems that are in the state, and now I have my first state, my second state, my third state, and so on. And these are ordered energetically, right? So in Schrödinger's equation, when you get your eigenvalues, you order them by, you rank them by their magnitude. And so the lowest, the smallest index, right? That's where you would expect the largest A. Most systems should be here, right? And then for the next higher state, you should have less, right? And less. Right. And so that gives you a distribution, right? So AJ, you can immediately see this number must be larger equals 0, right? Either there are some systems that have that state, or in the worst case, there's no system has the state, right? As you add up all the AJs over all your states, you're summing up the number of systems that occupy each state. So this plus this plus this, right? And we could go all the way down to 0. That's basically the total number of systems. or this integral. If you consider this to be continuous, right? So the big question is, this is fairly abstract, right? We construct these, we had this discussions about the curse of dimensionality. We now talk about 10 to the 23 systems in some reservoir with identical systems, different states that can be occupied and so on. So it turns out, despite this level of abstraction, we can actually arrive at some statements about this AJ, right? So what is AJ? And this gets me to subchapter 2.2. There was a gentleman a little bit more than 100 years ago, named Ludwig Boltzmann, who solved this problem, okay? And it's quite intriguing, right? The way he did it is very elegant. It's not, you don't need fancy math, which again makes me rant about why don't we teach this earlier. So he said, okay, this number of the occupation, right? This should have to do something with the energy of that state, right? This must be some function of the energy of that state, okay? Now, the total energy of that state is, of course, something we'd like to know, but it's not, it's very difficult to deal with that, right? To look at that. But maybe it's easier if we knew the ratio between two of these, and we also call them occupation numbers. So two of these numbers. So can we AJ over AK? Is that something we can do, right? So this is the ratio, and this ratio should then also be a function of the two energies, okay? Now, this is not just a function of the absolute energy, but it's rather a relative energy, right? So we did the separation ansatz, right? And so this results in additive expressions for the energies. Now, the ratio between these occupation numbers ought to do with the difference in energies, right? So this relative ratio is a function of these two, and it should be about the relative energy. So it should be a function of EK minus EI. Okay. Now, are there any questions so far? Yes, please. Oh, yes, of course. Thank you so much. Yeah. I'm sorry. I'm getting carried away. So something terrible is going on. This clock is not right. It's already 4 p.m. I will not tell you the answer now. It's a total cliffhanger. And I hope you won't sleep until Thursday when I tell you more about it. Thank you so much for your attention.